Welcome to Chapter 11. We're going to introduce a new test, and it's called a chi-squared test. And a chi looks like a curly X. So we do break the rule that we only use Greek letters for population parameters, but here it's a test statistic. And it's a very common notation for this type of test. And so again, we do have exception to the rule. So in Chapter 9, we looked at proportions for two groups, and we looked at a success or a failure. So we looked at two levels and two values. So we did proportions. We looked at comparing two proportions, and we could do proportions when we are dealing with categorical variables. So now in Chapter 11 we have two or more groups of a single variable, or we have two or more outcomes. So we're going to deal with categorical variables. We're going to put them in tables. We're going to look at the cells. We want to see if observed counts agree with some claimed distribution. And that's what we're going to do first. So that's the goodness of fit that we're going to do in 11.2, and then in 11.3 we're going to look at contingency tables, or they're also called two-way tables. And so we're going to look at two or more rows and two or more columns. This uses the chi-squared distribution, and the chi-squared distribution is a skewed distribution. Now what happens, it is skewed to the right, so the tail extends off to the right, and we will, as the number of degrees of freedom increase, the distribution becomes more symmetric. But all of our tests will be right-tailed tests when we do our chi-squared statistic. Now, the values can be 0 or positive. We don't have any negative values. The distribution is different for each number of degrees of freedom. And as we said in the last slide, that as that number goes up, the chi-squared distribution does approach normal. In Table A4, that's on your yellow sheet, or that is in the back of your book, you can find the area to the right of a certain chi-squared value. You can use Table A4 to find your critical value, but we're going to focus on StatCrunch, and we are going to use technology to help us out here. So Table A4 can be found in your textbook on page 773, and it's the area to the right of the critical value. So again, we started inferential statistics. We looked at how we estimate parameters for single populations, and then in Chapter 8 we looked at hypothesis testing. In Chapter 9 we looked at hypothesis testing involving two populations. So, and then in Chapter 10 we looked at correlation or regression using paired data. What we're going to do now is we're going to focus on categorical data. So let's start with goodness of fit. So we want to see if the data supports a known frequency distribution that's been claimed. And so we use a goodness of fit. So some things we need. When we talk about O, that's our observed value. E is our expected value. K represents the number of outcomes or categories, and N represents the total number of trials. Things that have to happen. Again, and I know this is not a surprise to you, but we have to have random data. And our data is going to be frequency counts. Now, our expected frequency has to be at least 5. Not your observed, but your expected. If your expected frequency is not at least 5, then you need to combine some categories. So here is the formula for calculating your chi-squared test statistic. You're going to take your observed value minus your expected value and you square that divided by the expected. You do that for each cell in your table and then you'll add them all up and that sum becomes your chi-squared statistic. So what happens if your observed and your expected are far apart, your chi-squared statistic is large. If they're close together, your chi-squared statistic is small. Now you can find your critical values using table A4, and you can use that to test, or we can find the p-values using StatCrunch. Our tests are always going to be right-tailed tests. Now sometimes all your expected frequencies are equal. Then you add up the observed frequencies and divide by the number of categories. So example, in your textbook, when you are looking at frequencies, for instance, if you are looking at expected frequencies for the births of girls among 100 births, you would know there's 2 categories. So 100 divided by 2 is going to be, you would expect 50 girls. We'll look at this in more detail when we actually do some examples. Now sometimes not all the frequencies are equal, and then your expected is the number times the probability for that category. And again, as I said earlier, if your observed and expected values are close, then you'll get a small chi-square value and your p-value will be large. That will be not statistically significant. If you have a large disagreement between observed and expected, then you're going to have large values of the chi-squared statistic and a small p-value. And if you have a large enough chi-squared statistic and a small enough p-value, you're going to reject the null hypothesis, because remember, the null hypothesis is always there's no difference between the observed and the expected. And remember, if p is low, the null must go. Now here is a visual of what we just said. If our observed and our expecteds are far apart, our chi-squared statistics is going to fall up here in the rejection region. And so the model's not a good fit. So we can throw out the null hypothesis. If the observed and the expecteds are close together, our chi-squared is not going to be in the rejection region, so we fail to reject and we assume that we have a good fit. Here's an example. A random sample of 140 births from local records was collected to show that there are fewer births on Saturdays and Sundays than there are on weekdays. So let's think about what we have. So here we have our data, and you have the number of births on given days of the week Do these data give significant evidence that local births are not equally likely on all days of the week? So let's think about it. If the births were equally likely, 1/7 of the births would happen on each day. So our null hypothesis is going to be that the probabilities are all equal. So the probabilities are the same on all days. And this is how we could write it, that all those probabilities are equal to 1/7. Now we need to calculate our expected counts. So since we had 140 births, we're going to expect 20 for each category. So here's our expected, here's our observed. And so by hand we could calculate our chi-squared statistic. And I want you to notice that we get 7.6. Let's go to StatCrunch and let's do the same data. Okay, so I put the data into StatCrunch, and let's go ahead and I'm going to go Stat Goodness of Fit chi-squared test. And my observed column is going to be observed births, and the expected column I don't have expected, so I'm going to do all cells in equal proportion. And I want to display those expected counts, and let's go ahead and let's do compute. Here is my data. So notice I had 140, my degrees of freedom was 6, my chi-squared statistic was 7.6, and my p-value is 0.2689. And notice I have my observed and my expected counts. So let's take this and let's go back to our PowerPoint presentation. Let's go back to the slides and let's see how this is going to work for us. Okay, so we've calculated the chi-squared statistic. We got the same thing on StatCrunch. And what is our conclusion? So our p-value, if we looked it up on the table, and it's not table E, it's the p-value is greater than 0.25. We found that on our StatCrunch page. And so we're going to fail to reject our null hypothesis. There's not significant evidence that births are not equally likely on all days of the week. Or, I would like to put it in positive, there's not sufficient evidence that births occur at different proportions on different days of the week. We could say that too. Now, our test statistic doesn't fall into our critical value, and this picture's from a different set of value. Oops, sorry, table A4, and we want our area to the right to be 0.05 or less, and so our critical chi-squared statistic in our case would be 12.592, which our chi-squared statistic didn't get close to that. So that's goodness of fit. Let's go ahead and let's look at a couple other problems for this section, and then we'll go on and talk about contingency tables. Let's look at this problem from your textbook. So this is number 13. It's on page 614 in your book. And so we look at the frequency of wins for different post positions in the Kentucky Derby horse race. A post position of 1 is closest to the inside rail, so that horse has the shortest distance to run. And we're looking at the first 10 post positions. We want to use a .05 significance level to test the claim that the likelihood of winning is the same for the different post positions. Based on the results, should bettors consider the post position of a horse racing in the Kentucky Derby? Let's go ahead and let's open up StatCrunch. And here's our data table. So here we have it, and if there was no difference, we would expect them all to be the same. So let's do stat, goodness of fit, chi-square. My observed is going to be in my wins column. All cells in equal proportion. And I want to do my expected value. So let's go ahead and let's compute it. And you can see that I have a chi-squared statistic, I have a p-value. So now it asked us to use a .05 significance level. So let's do that, and let's do a 6-step test. So here I've gone ahead and pasted in part of our results table from StatCrunch, and let's go ahead and let's do our 6-step test. So step 1, my null hypothesis is going to be that all p's are equal, and then my alternative hypothesis is going to be that all p's are not equal. And I can go ahead and so I want to do step 2, alpha equals, and step 3 is my data. So I'm going to take my table and put it in there. Step 4 is my chi-square statistic. So I'm going to say my chi-squared it's under symbol. If you want to do this, you can find your Greek letters under symbol. There it is. And it's a lowercase c. And then I want to do square equals 13.19. My p-value equals 0.1541. And in step 4, my p-value is not less than alpha, so therefore this is not statistically significant. So step 5 is going to be reject toe. Fail to reject toe, sorry. And step 6 says these data suggest that the post positions, the different post positions at the Kentucky Derby have no relationship with the frequency of wins. That's how you do a 6-step test.